Hello, this is Dr. Jui Jacket Huang from Department of Chemical Engineering. In this module, I will show you how to solve ODE, ordinary differential equation, and in MATLAB, and also how to get the phase portrait. So I will use an example that include enzymatic reactions as example to show you how to build especially the .m function to record the ODE model, and also after we do the simulation, how to sample the data from the simulation result and using linear interpolation, and how to save the data in the .mat format. Also the phase portrait. And here are some modules you should study before you watch this module. So here's a brief introduction of ODE simulations in MATLAB. So there are several approaches to solve ODE. The first one is to type the equation in the editor as a function. So we call this function base. So we're going to get a model in a function. Right, another one approach is in Simulink, and then I will introduce this in the introduction of Simulink and solving ODE in Simulink later. So in the Simulink, and typically we represent the model, right, using the module from the Simulink, and then link those modules together, and then to get the model, right, this ODE model. So just like the kids playing Lego, so you get all this plus, minus, all this mathematical module from the Simulink, from the library, and then link them together, right? So the difference between these two approaches and the function-based approach, and is the one we're going to discuss today. And actually, it's faster if you know how to do it. And the Simulink-based, right, those Lego playing approach, it's easier to pick up, but it's more time consuming to solve the ODE. So these two approaches, right? In addition to those, right, we also have another approach we call Laplace transform approach, and I will show you the detail in this Laplace transform and expression to solve linear ODE and that module. But the Laplace transform approach is limited to linear model. Okay, so today I'm going to show you the first approach, function-based approach, and it's not limited to a linear model. It can be used to solve any ODE model, right? Okay, so now I want to use this enzymatic reaction as example to show you how to build a ODE model in MATLAB, and also how to do simulation. So E is the enzyme, right, just like the catalyst, right? S is substrate, so the enzyme and substrate binds to each other and then form a complex, and then this complex release the enzyme back to the reactor, and but change the substrate to the product. So we could simplify, right, and from the substrate to the product, right, and right, and then well, there's some conditions for this simplification, but it's out of the scope of this module, right? But you could check, right? You could check. Mutually maintain kinetics, right? For the simplification. Okay. Anyway, so this is a biochemical reaction. Even it's not. So if you work in mechanical engineering, you could get similar, right, ODE model like this. So it doesn't matter what processes, right, what disciplines you're working on, and finally we're going to represent the concentration of the components, right? And using the ODE model like this. And then so before we implement the model in MATLAB, we're going to translate the model in the standard format. For example, we represent CE as S1, right? S2 actually is CS, right? S3 is CES, S4 is CP. So based on that, we write the equation on the right hand side, and then that is the one we're going to input in MATLAB. Right now, so to simulate the ODE in MATLAB, the first thing you do is you get the ODE model, right? You get the ODE model, and then you translate in this standard format. Right, you know what's S1, S2, right? S3, S4. And after that, we're going to input the model in MATLAB. Okay, so what we're going to do is we're going to create a function and to represent the ODE model. So for example, just like this function and end, right? And this the time, this the variables. For example, here x, right? And then this other parameters, right? For example, here we get k1, right? K minus 1 and k2, and they are parameters. Typically they are constant. So typically, right? So after that, so this is the derivative vector. We could calculate the derivative vector here. So this is ODE, right? Equation. So you just type ODE equation here. Okay, and after that we get the ODE model. So for example, for this enzymatic reaction here, so we could represent this ODE model here, right? So this one is ds1 dt. The second one is ds2 dt, ds3 dt, ds4 dt, and then you just type the equation here, right? So just type, for example, for ds7 dt you get, right, minus k1. So we k1, and we recall k1 as parallel 1, right? As a vector, parallel 1 is equal to k1, parallel 2 equal to k negative 1, parallel 3 equal to k2. So after that we get this must be k minus k1 s1 times s2 minus plus k2. Right here is actually it's s3. This should be k minus 1, like k parameter 2 is k minus 1 plus k2, right? So you can see this is the same as this term, right, on the right hand side. So you just type the equation into the function. But similarly, you get ds2 dt, ds3 dt, ds4 dt. So therefore we get the ODE model here. Alright, so we get, and here so ds dt is the derivative, right? So each one we get so you can see this is a column vector, right? Column vector, right? ds dt. We need to return the derivative for the ODE simulation. Okay, so after we type the ODE model and then we will save it. Let's remember we save the function, right, in the same name, right, in the document. Okay, now let me type the function, the ODE model here. So I'm going to build a new function, right? So the plus here, so I put function DSDT enzymatic reaction. T is the time, X is the variable, and then we have parallel, and then N, right, for the function. Okay, and then we got DS. So tips, I have indentation, right, to show the difference. Right here, DSDT, this is one column variable. So the first row actually is DSD1. We get right minus K1, so it should be minus K parallel 1 times S1. So you need to put a parenthesis here, right, because X also is a vector. 2 plus S3 times parenthesis parallel 2 plus parallel 3. Okay, so we're done with the DSD1. So similarly, you're going to get DSDT21 equal to minus parallel 1 times S1 times S2 plus parallel 2 times S3. Anyway, we assume that we already have the ODE model, so you are not required to develop ODE model here. But the module here just show you how to solve and a known ODE model in MATLAB. Okay, so this 3dt, right, you get parallel 1 times S1 times S2 minus S3 times parallel 2 plus parallel 3. So S3 is done. Now let's go to DS4 dt. So we get parallel 3 times S3. So we're done with ODE model. So you save it as the same thing as the function. Right, so we're done with the ODE model. Okay, now I want to show you how to solve it. So there's a multiple ODE solvers. Here I want to give a brief introduction. So typically this format we typically use to record the ODE model in the main function. So we're going to build a main function right here. So we're going to build a main function. This we call the main function. And then this is the ODE model. This is we call function. Right? We're going to build a main function to record the ODE function and then to do the simulation. There's a multiple solver. So typically we could separate the solvers into two groups. The first one is non-stiff, another one is stiff. Right, so stiff means what? Stiff means the variable. So for example, the S. So here you can see and change very fast with time. So we call this stiff, right? And actually it's some. So this one, the pink color one, change very fast, right? And in this time area, but the blue one change slow, right? So one change very fast, one change pretty slow, and then the time scale is very different. So we call this stiff model. So it's changing to solve the stiff model because typically when we solve ODE we use numerical, right? In numerical approach, right? So in MATLAB typically use a numerical approach to solve the ODE, right? So we need to discretize the model. So it's not that easy to determine a good step size, right, for the stiff model, right? For example, here for this area we might use a very small step size, right? And then for this area we might use a large step size. Anyway, if the model is stiff, means the variables have different time scale. One is very fast, one is very slow, and then it's changing to get a good step size, to get the system converge, and then to solve the ODE model. Okay, anyway, if you're not sure whether the model is stiff or not, I will suggest you to use ODE 15S, right? So S means right, also this one means stiff, right? All of the models for stiff models. So if you're sure a model is not stiff, you could use the ODE 45. This is the common solver, right? So you might ask me, how do we know whether the a solver works or not? So for example, if you use the ODE 45 to solve a stiff problem, and then the simulation will take a long time and very slow. So when you do this solve the ODE and then you find the simulation pretty slow, this means that you might need to change the solver, right? You need to change solver. For example, you could change those stiff server. So if your program run very slow and you want to stop it, you just push the Control plus key on the keyboard and to stop the program. Right. Anyway, so this is server, and then ODE function. So we just put ODE function after this @ sign. This means what? Means the handle of ODE equation, right? So we need to tell MATLAB that where we save the ODE equation, and here we also need to specify the time span. Time span means the time we want to do the simulation, right? So here initial time T0 and final time is TF. S0 is the initial condition of the variable x, and also you also can specify the parameter here. So auction typically is some parameters we can specify for the numerical solution. For example, we could determine we would specify this maximum step size, right? Okay, so here is the typical standard format for us to solve ODE. So T record the simulation time, S record the output, right, from the ODE model, and then this is the ODE function. So this is the server, right? So you could change to another server. So this is server, all right, and then you could get a time range, right? Starting time and then stop time, and then initial value, right? Of x for S0, and then here, so here is the anti-blanket. Anti-blanket is necessary because anti-blanket tips is used to determine those numerical solution auction, right? For example, the maximum step size. So if you don't want to change anything, so you just put the anti-parenthesis. So this means anti-parenthesis means no change in the numerical setting, right? So we don't change the step size, we don't change change the converge criteria, right? So here and also in the when you solve ODE, we could also specify other parameters here. So this is the standard format we use to solve ODE. Okay, so for this example enzymatic reaction, right? So here is the one we're going to use. So we could solve ODE using ODE 45. This enzymatic function, initial time and final time. So we change the time unit hour to seconds. That's why we times 3,600 here. So the initial value, right? Anti-parenthesis means we don't change the numerical parameters. Okay, setting. Okay, in parallel is the parameter, so we get here. So this k1, k minus 1, right? Typically, these parameters are given. So this initial value. Right, so this we call this main function. So we're going to build two functions. One is the main function, another one is ODE model, right? So you can see we're going to record the ODE model in the main function here, right? So you can see the ODE model's name here, right? So we build the ODE model first, right? Step 1, and then we write the main function to record the ODE model, and then do the simulation. Step 2. Now step 3 to plot result. Right, actually I already introduced all this the plot function in the module 1, right? So in the module 1 here, I already introduced the plot function here. So also for the data display module, I also introduced the plot function. So therefore, this is the color of the line, and then this marker, and this the type of the line. So I skip this part, right, because we already introduced it. Okay, now let's run the simulation, right? Actually this is the main function, right? And then we also need to type in the ODE model, right? So now let's type in the ODE model first, and then we type in the main function, and then we can do the simulation. Okay, so this one we function, right? dsdt, and then equal to enzymatic reaction, right? This t x parallel. So right, so I will save it right, before before you finish typing. Otherwise, sometimes your computer just crashes, and then you lost the program. So I will save it as enzymatic reaction. Maybe I say I already have one, so I change it to July. Okay. Maybe I still use the same enzymatic reaction. Oh, I already type in, right? Okay, so I don't need to type it again. Right, okay, now so we already have the enzymatic reaction now, and we will just run the simulation, right? Run the main function to run the simulation. So we get CLC Korea S0 initial value 0.1 for x1, 1 for s2, 0, 0, s3, and s4. So typically you get the initial value from the model, okay, and the parallel. So k1 equal to 0.05, k minus 1 equal to 0.001, and k2 equal to 0.1. Now, right, let's do the simulation. So the simulation is you get t save the time, x save the variable, right? ODE 45. So this enzymatic reaction, the time frame is 0. So the time unit actually is hour, so I changed to the second. So we times 3600, and then you get S0, right? And then this is the auction value parameters, right? This parameter. Okay, after that so again I will mention this is change the time from hour and to second, because the rate constant is so k1, k minus 1, k2 in the unit of second, right? And also here, so after you do simulation, you're going to get T is one column, then S actually is a matrix. You have S1 in the first column, S2 in the second column, S3 in the third column, S4 in the fourth column. So that's why we're going to plot the data column by column, right? Okay, now so we got plot T over. So we change the time unit back to hour, right? And then you get S and 1. The color for this one is black color, and then the line width is 2. So here's line width, right? So again, we want to plot multiple profile together, so that's why we need to use hold on. So here is hold on. So I just copy other lines here. So we get this should be 2, and this should be B, right? Blue color. And then I have 3 and 4. This is 3, right? And this is red color. This 4, and then we get C is cyan color, right? And then I put the S limit and Y limit. So define the range of X and Y in the figure, right? S limit I want to show from 0 to 1, so 1 hour. So Y limit from 0 to 1.2. You can change the value later if you want. So S label, we get the time in the unit. So every time when you plot the profile, you should specify the unit, right? And then this is the font size equal to 12. So similarly, you get Y label, and then you get component concentrations. You get below molar. But you also can change the font size to 12, and then so you could set GCA means the figure, right? GCA means the figure, like the figure handle. So you could change the figure, you could change the font size here, or this one, and by using GCA. So we change GCA, and here we get GCA font size to 12, and then the last one is legend, right? We have to show which profile represent what, right? Legend. So the first profile is for M size, second one is for substrate, and then number 3 is for the complex ES. The last one is for the P product, right? Okay. Sometimes for some MATLAB it doesn't work for the font size here, so I just don't type it here. Okay, save it. I say this is main M size matrix. Okay. Now, anyway, this you could change font size or not, right? But for some MATLAB program doesn't work here, so I just delete it. Right? You could type in and see what happened in your MATLAB. It's saying something wrong in my program. Let's see. So after this should be 4. Okay. So save it. Run it again. Let me double check the program. Check the initial value. Okay, so typically I think the model has some issue here, right? Let's check the model. Model something wrong in the model. So it should be 1 and 2 here. So this is 1 and 2 here, right? So 1 and 2. Double check and make sure that it's correct. Okay, save it, and then we run the program again here. So now we have beautiful profile, right? But we don't have the legend. Let me see. So here, for the so this should be font size, not this should be font size, right? Okay, now run it again. So this is the profile you're going to get, right? Okay. So we are done with the so here there's other information actually already introduced for the block, right? The module in the first module, right? Also you could see here as a label, y label. You would put a title here, so if you put the title should be around here, right? Okay. Now in some case scenario, right? For example, you want to sample the simulation result at specific time points. For example, you want to quantify, right, the error. For example, this is model prediction. This is experimental data. Experiment, right? So therefore, right, we need to sample the data at specific time points. For example, I want to sample the data in this time point. So what should we do, right? And typically you're going to use here this is the function you're going to use because interpolation is a linear interpolation, right? So here's interpolation. This is a 1, okay? This is a number 1, not letter L, right? So some of you may mistake here. All right. So for example, we want to sample the data, sample the S1 data. So this is the time and S1 profile, and then this is the time point we're going to sample. Again, we're going to change the unit, right? This is the hours. This is unit in hour. We change the unit to second, right? So therefore, we get sample data S1, S2, S3, S4 at all these time points. So after that, we're going to plot the data at the sample time point, right? Okay. So here we also want to use the marker to show the data point, right? Okay. Now let's type this in the model. Okay. Now we do the sample data from the simulation result. Right. Okay, now let's type this one, time sample time point equal to 0.1, right? Increasing intervals 0.1 into 1, so S1 equal to into P1, right? This is 1, make sure, and then we get T as time, so X1, and then with time point times 3,600, right? This is the sample of S1 at this time point. So similarly, we could get S2, S3, S4. So I just change the 2, right? 3, 4, 4 here, right? And after that, I just plug the time point as 1. Now I just key, right? It's black color, and this marker, specify the marker, right? So this line width. Okay, so this one we get, and then we get hold on, and then you could plug the same thing. I could put a figure here, right? So put a figure here, put a figure here because I want to keep the first figure here. So the first figure also put a figure here. Means that we open a new figure, right? And then we don't erase the original figure, the previous figure, right? Okay, now we could plug for S2, S3, S4, right? This S2, the color for S2 is blue, right? This will be S, the fence, the marker, and then we get S3 here. Then we change the color to red color, and then the marker right here change to a circle. Then this 4. Then the markers as the the arrow. So similarly, we could just copy all this one as as limit, y limit, and the labels and the legend. Delete, hold on here. Okay, save it. Right, and then we could run the simulation. Right, this is the result we get. So so here's the profile. Alright, so you can see the sample data point here. So typically, when we after we do run simulation, we would like to save the data. So for example, this t, this x, we save the data in the dot, right, MAT format, and then so in the future you don't have to rerun the simulation to get to plot the output profile. So this is how you save the data. And if you want to load the data in the future, right? So you load the data, and then this one actually we call this is structure, right? This one kind of data format. So you can see the structure has 2 variables, t and x. So you just use, right? So the structure's name, and then dot t, and then you get a t value, and then you get structure dot s, you get an s value. So you can see again we have all these 4 columns here, right? And for different variables. Okay, now I want to show you how to save the data, right? So if you want to close all the figures, you type close all, right? Okay, now let's save the data. So save the data, and in the MZI matic data.mat, and then we get t, x. So we save it. So now let's run it. Right, and then you could see the data here, right? MZI data. Okay, now let's load it. Right, so we just load it. Data load, and just type load, type the name of the data. Right, and then you will talk, so you get data load dot t, change the unit to hour, then data load dot x, right? This is the x value, the first column, and then the color is black color, and then change the line width, maybe 2, and then you put hold on, and then copy this, for S2, S3, S4. Just change this one to 2, and then this blue color, this 3 should be the red color, and sign color red color. This 4, this is 4, this sign color, and then I just copy the S label, Y label, electron, right? So copy all this stuff together. All this. Okay. Then save it, run it. So you guys get a profile like this. Alright, okay. Oh, I should put a figure here, right? Because we open a new figure, so put a figure here, and then the new figure will not overlap with the old figure. And so we have 3 figures. See, this is the new one. This one we got it from the data. The last one, figure 3. Okay. So we are done with the data saving. Now I want to show you how to plot the face portraits. So all the profile so far, and actually we had the time, right? So we plot the output variables and versus the time. Now I want to show you another type of figure. Actually, we want to show the relationship between, for example, 2 variables, for example, substrate and product, right? Under different conditions, for example, under different initial condition of the substrate concentration, and we call this as phase portrait, right? So here's a procedure to ask to get the phase portrait. So we changed the condition, for example, the initial concentration of substrate, and then we run the simulation. And then after we run the simulation, we get the data for example, P and S. And then we plot, right? We plot the right, P versus S. So for example, P in the X, in the Y label, and then S in the X label, right? And then we hold on this profile. Then we go back to step 1. So we change the condition again, right? We change the initial condition to another value, and then we do that again. So for each initial value, for each change condition, we do the simulation, and then we plot the 2 variables, right, in one figure until all the conditions have been tried. So we call this phase portrait. Okay, now here's the example. So now we want to plot the profile of P over X, right? And P over X, and then we change the substrate initial value from 0.1 to 2, and then the interval equal to 0.1, right? So we don't change, right? And then we set the initial value for all other variables, no change, and then we don't change the parameter value, right? So you can see, so for each initial value, right, we change the substrate initial value, and then after that we run a simulation. So we change this initial value here, we run a simulation, and then we plot S versus P, right? Okay, so as you can see, S is the second column, P is the fourth column. Then we put hold on, and then we just get this profile like this. Right, the straight line means what? Means all S is converted to P, right? In the reaction, in ideal as in the area. Okay, now let's type this program together here. So I may build a new program because the original one is too long. So let's see it, right? Let's save it as main. Alright, face portrait. Oh, there's a typo. Here's should be portrait. Let me see. Change the name. So I change the name here. Okay. Okay, I open it and then type the program. Right, so we change. Actually, we copy the program from the enzymatic reaction. Let me see. So main so we could copy here. All these ones should be the same. Copy. Right, and then so we set the initial value as 0 equal to actually right, change from 0.1 increasing by 0.1 to 2, right, and then we do the for loop for I equal to 1 and to the length of S0, right, and then we copy the simulation, right, ODE simulation here. So we could copy ODE simulation here. Just copy from the main enzymatic, right? And then what we need to do, we just change the initial value of the substrate. So we get S0 2 equal to S02 equal to S0 I, right? So we change the initial value of the substrate. So after that, we plot the substrate and versus the product, and then we just put hold on, and then here's the y label, s label, right? So s label, we get substrate right, and then we put the font size here 12. Okay, so similarly we get the y label. Here should be product, and then we could put the s limit here. Maybe we want to do simulation, show the result from 0 to 2, right? Because we changed the the initial value from 0 to 2, right? Okay, so we save it and then we run it. Right, here's the result we should get. Okay, so we're done with this module.